Cedric Ringenbach, who's the CEO of the Shift project, will present some learnings from Rainer Kümmel's work and how you can use that to be policy prescriptive.
So thanks a lot for to the organizer for inviting me. I think that they are afraid that there was Rainer Kümmel and there will be Gaël Giraud after, and they thought it was too much mathematics in a row. So I put me in between, and you will have a rest for that. Because of that. There will be a little bit of mathematics, but we will quickly go back on what Rainer already said, and then I will spend more time on what consequences we can, the conclusion we can draw from this work. Okay, so first thing, we will not debate about that, but the idea when you talk about production function is that you cannot decide what GDP will be. So it's kind of nonsense to use it as an external value, as an exogenous value when you put that in a model. So when you work with a prediction function, it means you use the GDP as an endogenous value because you think it will depend on some factors, especially energy, and that's what Rainer has found and has measured. So here, some prediction function, just as example, it started with solo function where he needs the residual to complete, to make it work. Then we understood that energy is important, so we can add energy. Robert Ayres did the work with useful work instead of energy or exergy. You can add matter if you want, material, other resources, and you can add creativity. But here we will focus on the clay function, which is only capital, labor, and energy. And especially to make an example, we use the Cobb-Douglas function, which is the simplest one among all the different mathematical solutions. This one is the simplest one, so it's okay for me. So K stands for the capital, the physical capital, the machines that you run to run the economy, and the labor, and the energy. So you need all of these three guys to do something like, for example, to grow corp. Then, for practical reason, we can also use this mathematical way of putting things. And you see that we are in a 3D space, and it can be more practical to write things. One important thing about prediction function is that each factor is essential. You cannot have any prediction if one of them is equal to 0. For example, if you say that you try to produce without the capital, then there is no prediction. Without the guy operating the machine, there is no prediction. And without energy, there is almost no prediction. Rainer said that before, the derivative has to be positive. Otherwise, it's just not a prediction factor. XY, if you have this derivative that is negative, then XY is not a prediction factor anymore. It's a destruction factor. It's almost the definition. Then the second derivative is negative. Why? Because if you keep all the factors constant and you move only one, you change only one, what happens? For instance, you have all the three guys here and you add more oil. Okay, maybe the guy will run the truck a bit faster, but it will not increase very much the production, just because you have too much oil. I mean, if you're not able to use it, then it's useless. If you have two guys, well, they will not be together on the truck. Or maybe we can take turn, but I mean, it's not proportional. The production will not double because you have two guys. And if you have one guy and two trucks, I can make you I don't make you a picture, but you will not be able to drive both at the same time. So that's why this derivative, this second derivative, is negative. You understand it quite easily. Intuitively, you understand that now. But if you double everything...
And with energy, because one factor may
Yeah, but you cannot run the track faster than it can. So at a certain level, too much is too much, and you cannot use it because the other factor is essential. Constant return to scale is when you double everything, then it works. If you double everything, you double the production. If you have 2 guys, 2 trucks, and twice much. And 2 of course. Yeah, it's a good remark. If you have 2 Earths, you can double the production. Yeah, exactly. We don't talk about the limits here. So that's an illustration of constant return to scale. Now I will tell you a bit more about what substitutability is. There is a little bit of substitutability between factors, and that is important in order to evoke the cost-share theorem. You don't use the cost-share theorem if you don't have substitutability. So it means that you can use a little bit of one factor if you have a little bit less of one other. For example, if you go from this kind of technology and you put robots instead, then you will have less labor, more capital in order to produce the same thing. So that's automatization. And so Rainer talked about it. And today there is a big incentive to go in this direction. We will see why. If you go from this technology to this one, then that's more labor, and that needs more energy. Okay, so this is the same with this, a nice bike and a little motorbike. So for about the same amount of capital, but this is a very good one. It's an expensive one. It's as expensive as this one. So for the same capital, here you will need more labor, and here you will use energy. And substitutability between energy and capital is when, for example, you need to heat your house, and instead of that, you insulate it more. So you need less energy, but you need something that you can call a capital, which is your insulation. At the same time, when you go from fossil energy to renewables, here what you need is capital. The wind is free, of course, but the wind wheel is not free at all. So because of this substitutability, we can evoke the cost-share theorem. Is this the next one? Yes, but substitutability, of course, has limits. For example, you cannot say that with the production function, you can get rid of energy because you change it with capital. You need all of the factors. If 1 equals to 0, then you will not be able to replace it by infinite of something. But it's meaningful if you keep around the point where we are today. We are in a 3D space with KLE today at one point. It's a state function, as we say. And if you keep around this neighborhood, in the neighborhood of this point, then you can use the prediction function. It will be quite a good approximation of how you can increase your GDP or maintain your GDP. So that's a question of notation. I give again the definition of the elasticity because we will need it. Elasticity is this term. So it's the power here when you write it in the Cobb-Douglas way. And if you use a logarithmic derivative, is this term in front of all the of each factor. So now we have. So that's the definition then of the output elasticity. That's the power in front of each term. What is the cost-share theorem? It says, right now, tell me if I'm wrong. I think I copied it from your book, but at the equilibrium, the output elasticity of a production function is equal to its cost share. So for me, the reason why it's not true is just that we are not at the equilibrium. We are not in the equilibrium. Yeah, we are in a world that is changing, and for many reasons, it's not the state. It's not the case yet. But maybe we tend toward this theorem because it's normal. I try to make you feel why you have the theorem. if you have the choice between a machine and a human, and the machine is less expensive, then you change for the machine. So you have this substitutability that exists, and according to how much it costs, you choose one or another. Then it's like a market. There's a market for labor, there's a market for machines, there's a market for energy. So as markets, demand and offer tend to set the price, and at the equilibrium, if there is a factor that is very much useful for you, then you will be able to pay a lot for this factor. And we will see that at the equilibrium today, well, not at the equilibrium, and at the moment we are not paying the factors as the same way as they are useful for your production function. But this is an equilibrium maybe toward which we are tending. And these has very important consequences. So we have our an economy that is here and that uses some the three factors here, and here we see the cost of each factor. So the capital is only 25, the labor is a lot, is 70, and energy is only 5%. And if we think that these are equals to the production, to the elasticities, then we think that energy is not very important at all for the economy. Okay. So that's what Rainer presented. He went through calculation through real figures on some decades. GDP, national accounting for capital, you add all the physical capital in companies, then you count the number of work hours, and then primary energy from the International Energy Agency. And from that, you calculate with a kind of least square method. I'm simplifying things. And you calculate elasticity, and you obtain this kind of result. I gave round figures because, when you do this kind of thing, I think you cannot have 5 digits numbers. It's a gross method, but it's important to have the order of magnitude. And here are the results. You see that capital is 40, it's a bit more than that. Labor is much less, and energy is tremendous. It's 1 order of magnitude more than here. So what conclusion do we draw out of that?
To understand, in fact, at the right, you have these are derivative of y over the quantity, such as the capital, for example. Am I right? Or not?
Here, the elasticities are, when I show the Cobb-Douglas function, it's k at the power alpha, and then k at then L at the power beta, etc. So here are alpha, beta, and gamma.
Which
are
derivatives of y?
No, they are not derivative. They are the constant in front of the derivative.
But how do you measure that?
Let's give an example. You say it's a Cobb-Douglas function. You assume they are constant, and then you try to fit these constants in order to find, like when you do a least square methodology. Sorry? You need to have time series with GDP and each 3 factor. And if you have that, you make an reverse engineering, and then you calculate your constants. Okay? Assuming they are constant. Okay. So, Rainer, what do we do with that? So here starts what I really intended to tell you. First thing is energy is undervalued in many models. So that's what Rainer already said, and that is very important. If something there is one message you can keep from this week, I think that would be good that you remember that the elasticity of energy is much more important than what people usually use. And maybe Gail will talk more about that. At least he's working on it with Zenep. That is a correlation between oil consumption variation and GDP variation during time. And you see that it's quite correlated. So we it's another way to show that the energy is very much important in the production function. Of course, you can say that is the cause and effect is not in this sense. You can say, okay, energy consumption increased because economy is doing well, but still you can also think that it's looped, it's closed looped. Second assumption that is that labor is overpaid. I'm a bit provocative, of course.
Every capitalist will love that.
Yeah. I show that in front of CFDT. And I'm still alive. So what does it mean?
We don't say that this should be changed, okay?
No, we don't, and we even say that it's on purpose.
Yeah.
This is Keynes and this is John Ford. So the idea is that we pay people so that they become consumer. And if you don't do that, there is no economy. You know, there's nobody to whom you can sell your production. So it's important to pay people, even if you don't really use them, because you could replace some of the workers by a machine. It's important to still have workers and to pay them anyway. Otherwise, the economy doesn't work. So we are already in an economy that works like that, in an economy where some rules, some laws do, the result of the laws and the rules that we have put are that we pay people for the work they do, and we pay them much more than what could be the result of a kind of market where you have these three factors, capital, labor, and energy, and you can choose between them on the kind of liberal market. So the economy is already not liberal from this point of view, and it's important to say it, and it's important to keep it like this. So we cannot substitute, energy cannot be substituted by labor. Why? Because you see that here the 10% is very low. And we also know that the power of the efficiency of our muscle is much lower than the one of energy and machines. So that's the reason why it's nonsense to think that we will replace energy by the muscles or by more work because of this elasticity, this little elasticity of work. Then, what is the next solution if it's not working? It's investment. Because the second factor after energy is capital. So the energy transition is this. This arrow is the energy transition. It's replacing energy by capital. And I will come back to the illustration of the substitution between energy and capital. Here you have fossil energy, and here you have, let's say, renewable energies, or you can have efficiency investments. And here is the whole picture of the energy transition. We go from stock energies to flow energies. So just make you notice that here is stock energy and flow energy, and here is energy. When you talk about energy as a production factor, it's a flow. You consume energy, and when you use free wind with a wind power, a wind turbine, then it's capital and it's a stock. So here is a flow, and here is a flow. Here is a stock. Here is a stock. So it's the other way around. Just if anything. So we need the energy transition is going from this world based on stock energy that we use, from which we draw a flow to feed our economy, to flow energies or no energy, energy reduction, that need investments in a physical capital. The physical capital will replace the use of energy. And I quote HSBC, who say in a recent report that we are moving from an OPEX to a CAPEX world. So it illustrates very well this substitution. And an investment will be everywhere in the transition. We will need to insulate houses. It's an investment. We will need to invent trucks or car that use less oil, and that's R&D, that's investment. We will need to invent a new process that use less energy, and everywhere we look, it's a question of investment. And I'm preparing the talk of Gael because we need, or maybe the last one, in fact, because here we feel the need for a big investment in money this time to finance the transition. Okay, fifth remark is a question about capital remuneration, because if we go from this world where energy is important for the economy to a world where we use more capital, then the way we remunerate them is very different, because if you when you pay for capital, it's a rent. You pay for example, I invest in a machine and then I get money from this investment along the time, so it's okay, it's good for me. While when you are a worker, you are paid every day for what you do, so it's a very different way of remuneration. So if we go toward a world where there is much more physical capital, then the remuneration of these different capitals will be in favor of the one that is the most useful and the most used. It's not only the most useful, that means it's the most useful, then it will be more used also, which is not represented here. Then it means we have less money to pay for the people who work. And I come back to the cost share theorem, saying that there should be an equality between cost and elasticity, and it says it at the equilibrium. So maybe we are tending toward this equilibrium, which means that maybe one day we will arrive in a state where cost and elasticity will be the same, and we will be somewhere in between. So it means that the elasticity of capital and the cost of capital will be around 30, and the cost and elasticity of labor will be around here, which is much less, so it's less money for the workers. And in energy, it is much more, and that we feel that we are going towards something like that. We feel we are going toward in a world where the price of energy will be much bigger. I mean, and the budget for energy will be much bigger in the world in which we are going to. So maybe we go to this direction, and this goes to the last remark, which is that almost the last, that we have to rethink wealth distribution because of the big role that capital is going to play in the world after the transition. And if we don't take that into account, we will fail, because the political measure that we propose will go against the interest of most of the people. Last thing is a question of short-term and long-term. We say that we need to put more money in the physical capital. We need to invest in the physical capital. That is called the gross fixed capital formation here. And it's around 20% today. And let's imagine that we need it to be 30 instead of 20. And let's imagine that the total production is capped, because you see today the growth is slow, the growth is limited. Let's imagine that you have no growth in the future, and we need at the same time to increase this formation of capital. Then this will be taken out of consumption. There will be competition between investment and consumption, and that's a short and long-term issue, because we need to make an effort in a short term here. So that's the scenario where the business as usual scenario, that we do the same as before, so we keep at 20%. And this is the transition scenario, so we need to invest very much in the capital in order to replace the use of energy. So it's going to be taken from the consumption. And that's bad news, but it's in order to prevent the collapse. This collapse is related to the fact that you did not invest in your capital, you have less energy, and then, which is still a very much important, very important production factor. So when you have less energy, or you need to make less CO2, so you use less energy, then your GDP will decrease. And see, if you want to keep resilient, we need to make this investment in order to have this resilience. So the investment is to be done today in order to preserve the future. And then I quote Jean-Michel Giraud, that has been quoted by Patrick Riquet this week. We have to solve climate and energy issue before the second half of the century, otherwise it's a mess. Thank you for your attention.